Welcome to this explainer on graphs of functions. Today, we're basically putting on our detective hats to investigate the hidden rules of mathematical relations. And more importantly, we're going to learn exactly how to track them in the real world. I'm incredibly excited to guide you through this because honestly, once you understand how to visualize math, it literally changes how you see everything around you. Here is our roadmap for today. 1. What is a function? 2. Identifying true functions. 3. 4 graph shapes. 4. Steps to draw graphs. And 5. Reading real-life graphs. We're going to build this step by step. Section 1. What is a function? Okay, let's dive into the mechanics. Now, you might already know that a relation is just matching items from one set to another. But a true function is strict. It's a very specific type of relation where each input has only one output, and every single element in your starting set gets included. It takes elements from one group and relates them so reliably to another that each input gives you exactly one predictable output. It's kind of like a perfectly tuned mathematical machine. And to operate this machine, well, we need inputs. That brings us to the domain. Just think of the domain as your starting point. It's the complete list of every single input you're actually allowed to feed into your machine. Then, on the flip side, we've got the codomain. The codomain represents all the possible destinations or outputs your function could potentially produce. It's essentially the whole universe of answers that might pop out. But you see, the codomain is just what's possible. The range is the actual tangible output you get. So, for example, if your function's rule is simply to square the number, so f of x equals x squared, and you input a 4 from your domain, your actual output, your range, is 16, right? Because 4 squared is 16. Section 2, identifying true mathematical functions. So now that we have our vocabulary down, let's break down the rules of predictability. Remember, a true function absolutely requires a single, reliable output for every input. That's exactly why one-to-one relations work perfectly. Many-to-one relations work too. Just imagine several different students all getting the same grade of an A. You have different inputs, but the same output. That is perfectly logical. But what about one-to-many or many-to-many relations? Yeah, no. If you put one input in and suddenly get 3 unpredictable outputs out, well, your machine is broken. They are way too chaotic to be called true functions. We can actually build a really clear visual profile of our function using a table of values mapping our inputs to our outputs. For instance, if set P maps to set Q and you see 1 mapping to 4, 2 to 5, and 3 to 6, the underlying rule is clearly just adding 3. And we can also represent this using ordered pairs, where we just group the input and output together in parentheses, like 1, 4, 2, 5, and 3, 6. And to summarize that exact same relationship mathematically, we just write it out as an equation. We use the function notation f, where f of x equals x plus 3. Or, you can simply write y equals x plus 3. In this setup, x is your domain input, and y, or f of x, is your range output. It's just a super clean, efficient way to write down the rule. Section 3. The 4 graph shapes. Visualizing the math is where things really start to click. Depending on the equation you're dealing with, your graph is going to take one of 4 totally distinct shapes. First up is the linear function, like y equals mx plus c, which always forms a perfectly straight line. Second is the quadratic function, and that creates a really nice, smooth, U-shaped parabola curve. Third, we have the cubic function, featuring x cubed, which draws this distinct S-shaped curve. And fourth is the reciprocal function, which forms a split curve known as a hyperbola. Now, the reciprocal function is super interesting, and it brilliantly illustrates a unique quirk in mathematics. Written as f of x equals 1 over x, its domain includes all real numbers except 0. Why? Well, if you try dividing 1 by 0, you literally break the math. It's completely undefined. And that is exactly why the hyperbola graph splits in 2 and never, ever touches the 0 line on the axis. Section 4. 4 steps to draw graphs. Okay. Let's roll up our sleeves and put these clues into practice. If you want to ace your graphing questions on exams, you need to memorize this highly logical 4-step checklist. It guarantees you never miss a beat. Step 1. Construct a table of values. Step 2. Draw and label your axes using the correct scale. Step 3. Plot your ordered x and y points. And step 4. Join those points to form either a straight line or a smooth curve, depending on whatever function type you have. Let's see how step 1 builds for a quadratic function, specifically y equals x squared minus 2x minus 3. We have to carefully calculate our y values for each x input to build out our table. If we input -1, we do the math. -1 squared minus 2 times -1 minus 3, which gives us 0. Oh, and here is a massive exam tip for you. Always be super careful with negative numbers here. Definitely use brackets if you're typing this into a calculator so you don't mess up the signs. Then you just repeat that logic for each input to complete the table. Now, before you rush ahead to plot those ordered pairs, here is another absolutely crucial exam tip. You must ensure your axes follow the precise scale requested in the problem. If the question asks for a scale of 2 centimeters to 1 unit on the x-axis, you have to measure that out exactly. If you just wing it and use a random scale, your whole curve is going to be distorted, and the relationships will be completely visually wrong. Section 5. Reading graphs in real life. So, interpreting a graph really just means reading the map backwards and forwards. If you're given a specific input, you just trace that x value straight up to the line on your graph to find the corresponding y output. Or you do the exact reverse. Start at a y value, trace across to the line, and then look down to find the x input. Let's actually apply this to something real. Imagine a physical experiment where a ball is dropped from a height of 4 meters. How can we use our graph reading skills to determine its exact landing time without ever touching a stopwatch? If we plot the movement of this ball on a graph and check our table of values, we can literally read the story of the fall. The x-axis represents time in minutes, and the y-axis is height in meters. At 0 minutes, the height is 4 meters. That's the exact moment it's dropped. And we can see that at the first minute, where x equals 1, the distance of the ball from the ground is exactly 2 meters. So, the crucial point here is figuring out the impact. To answer our question, we have to use some basic logic. We know the ball physically hits the ground when its height, y, is equal to 0. So we just trace the y-axis down to 0, look across to our curve, and check the x-axis. Looking at our data, when y equals 0, x equals precisely 2. Therefore, the ball touches the ground exactly at the second minute. No stopwatch needed. And honestly, that is the true power of understanding graphs of functions. You can translate complex, messy, real-world relations into these clear, visual curves that let you extract precise answers. Now that you know the rules, the shapes, and the steps to read them, I want you to look around today. Where else do you see variables moving and changing together in your own life? How many other real-world mysteries could you solve just by graphing their functions? Think about it and keep exploring.